Specialized domains like medicine, law, and engineering have almost no labeled data, and hiring experts to label it is prohibitively expensive. So how do you train a large language model for these fields? You have no ground truth, no stronger teacher to copy, no reward oracle. A team at the University of Pittsburgh found an answer hiding inside the model itself, not a cleverer reward. A way to pick which of its own unlabeled examples to trust. The method is called Neuron-Aware Self-Distillation, and it beats reward-based reinforcement learning at its own game, while also fixing the calibration that reinforcement learning breaks. The method has 4 stages, and only one place where the model actually learns. Stage 1 is data selection by neuron consensus. Run the model on an unlabeled example, record which of its neurons fire, and count them. The count is a consensus score. Few active neurons means sparse, unconflicted retrieval, which is more reliable and less prone to hallucination. Keep the bottom 20%. Stage 2 is context curation by neuron overlap. Compare 2 examples by the Jacquard distance between their neuron sets and retrieve the 10 nearest neighbors as a few-shot demonstration. Stage 3 is on-policy distillation against a moving average copy of the model, conditioned on that context. The loss is reverse KL, gradients flow only to the student, and the teacher is an exponential moving average with rate 0.01. Stage 4, because the context gets internalized into the weights, the demonstrations are not needed at inference time. The base model is Quen 3-4 billion, the thinking variant. They evaluate on Sino-Evil, split into biology, materials, physics, and chemistry, plus an education feedback dataset and MMLU professional. Neuron extraction takes the top 2,000 neurons per layer per chunk, then deduplicates to a global set of 5,000. Training runs for 150 steps of reverse KL on 4 GPUs. The baselines are the 3 families of annotation-free post-training, SFT self-training, GRPO with majority vote pseudo-labels, and a self-certainty reward method. Every method is evaluated with 8 responses per question, and crucially, they report not just accuracy, but expected calibration error. Why does counting active neurons work? Because the count correlates with being wrong. Domain accuracy rises monotonically with a normalized neuron count, correlation 0.369, p-value below 1 in a million. Per domain, more activated neurons means lower accuracy with negative correlations across biology, materials, physics, and chemistry. So picking low activation examples means picking examples the model already handles reliably, and reinforcing correct reasoning on reliable examples avoids amplifying the model's own hallucinations. And the moving average teacher matters too. It is a fixed target that smooths the noisy student, and because the context is baked into the weights, you never pay for demonstrations at test time. First result, accuracy on the education feedback dataset, in domain. The base model scores 65. SFT self-training nudges it to 67. GRPO does not move it at all. Neuron-Aware Self-Distillation jumps to 72, a gain of 7.2 points, the largest single improvement of any method on any source domain in the entire paper. Second result, calibration, measured as expected calibration error, lower is better. This is where reinforcement learning reveals its cost. SFT and GRPO both inflate calibration error, making the model more wrong about how confident it should be. Neuron-Aware Self-Distillation does the opposite. It reduces overall calibration error, and on education feedback it drops from 0.246 to 0.191, a reduction of 0.056. So on the exact domain where it gives its biggest accuracy gain, it also gets better calibrated. Accuracy and calibration improved at the same time without a single label. Third result, the cross-domain test, where you train on one domain and evaluate on the others. This is where self-training usually collapses and where reward-based methods forget. SFT loses over 5 average points cross-domain. But Neuron-Aware Self-Distillation keeps every single cross-domain cell positive, averaging plus 0.9. No catastrophic forgetting. The clean neuron signal generalizes. The noisy reward signal does not. Honest scope. First, this is a single model, Quen 3-4 billion, and a workshop paper, so treat the numbers as a strong signal, not a fully swept result. Second, the self-certainty baseline was dropped on the education run for showing no improvement, so its headline average is over 5 sources, not 6. Averaged fairly over 6, it falls below Neuron-Aware Self-Distillation. Third, selecting by activation count alone is informative but insufficient. The top 20% still helps some domains, which is why context curation and on-policy distillation are doing real work on top of selection. The takeaway, when you have no labels and no teacher, the best move is not to design a cleverer reward. It is to listen to the model's own neurons to decide which of its own examples to believe, distill against a smooth copy of itself, and skip the reward entirely. Better accuracy, better calibration, no forgetting. Subscribe for the next paper breakdown.